Hello, Professor. We could start.
Okay, let's start today's lecture. Let me start this lecture with a generalization. Of the Borel-Weil theorem, which we proved on the last lecture. This extension concerns line bundles over partial flag varieties. So if you have a connected reductive group G and a Borel subgroup in G denoted by B, let's consider an intermediate subgroup between G and B. So let me denote it by P. Such intermediate subgroups are called parabolic subgroups. Okay, and to such a subgroup, we can associate a homogeneous variety, G modulo P, which is called a partial flag variety. Or maybe better to say generalized partial flag variety. Generalized, I put it in brackets, partial.
Do we need any topological restriction on P, like P should be a closed subgroup?
Yes, of course. When I consider subgroups, I usually mean algebraic subgroups, means closed in Zariski topology. You are right. Maybe I should write it explicitly, but let me skip it for the sequel because it takes time to write to say it at any time that it is closed. Let's assume by default that a subgroup considered in an algebraic group is assumed to be a closed subgroup, that is an algebraic subgroup, okay? So this is a generalized partial flag variety. Partial flag variety. Why this name? Because if G is GLN, the basic example of a connected reductive group, then such kind of homogeneous spaces are indeed partial flag varieties, varieties consisting of partial flags in an n-dimensional vector space. So, excuse me, yes, I put this. So for an arbitrary reductive group, we call it a generalized partial flag variety. And suppose I'm restoring the notation from the previous lecture. So suppose a character lambda of B of the Borel subgroup extends to a character of P. Then, of course, we can associate with this character of P a homogeneous line bundle. Let me denote it as script L sub P, comma, I want to associate it with the character minus lambda as before. This is a homogeneous line bundle over G mod P. So this is G cross over P with a one-dimensional vector space on which P acts via the character minus lambda. Okay, the same thing as we did for the Borel-Weil theorem. And the following statement is actually a corollary from the Borel-Weil theorem that the space of sections of this line bundle over G mod P is again either zero. This is the case if lambda does not belong to the positive Weil chamber. Or it carries on an irreducible representation of G dual to that of highest weight lambda. So an irreducible representation of highest weight lambda star in our previous notation. This is if lambda is a dominant weight, if it belongs to the positive L chamber. So the same statement as for line bundles over G mod B, but now we have line bundles over a smaller variety in a sense. This statement can be proved independently along the same lines as the Borel-Well theorem itself. But let me deduce this as a corollary from the Borel-Well theorem. So what is the proof?
Hey, Professor, I want to ask a question.
Yes, please.
Well, the Borel subgroup is not a closed subgroup, right?
No, Borel subgroup is closed. It is an algebraic subgroup. It is closed. Of course, it is closed.
Closed? Well,
yes, yes. All subgroups here are closed in G. In G, not maybe I mean maybe you are confused with this example of full matrix group GLN. Then the subgroups are closed in GLN, not in the space of all matrices, but they are closed in GLN.
No, I know.
Yeah. Okay. So how we can deduce this statement from the Borel-Well theorem? Let us consider G mod P as the base of a fibration with total space G mod B. So we have a natural projection map from G mod B to G mod P. Let me denote it as pi. With typical fiber P mod B. Okay? So if we restrict the line bundle, which I denoted as L minus lambda, L sub minus lambda in my previous lecture, this is a line bundle. This is a line bundle on G mod B. This is a line bundle on this guy. If I restrict this line bundle to the typical fiber, P over B, then I get a homogeneous line bundle on this smaller variety. So this is P cross over B with K sub minus lambda. But recall that I gave you an exercise on my previous lecture that if you have a homogeneous line or even vector bundle such that the action of the stabilizer on the fiber extends to the action of the bigger group, and this is the case here because we have an action of B on this one-dimensional fiber, but by assumption it extends to the action of P, since lambda and minus lambda as well are characters, can be extended to characters of P. So we are on the assumption of this exercise, and this exercise, exercise 1 from previous lecture, exercise 1 tells us that in this case this homogeneous line bundle is trivial. It is isomorphic just to the direct product of P over B and this one-dimensional fiber K minus lambda, K sub minus lambda. And also this variety P over B is a projective variety. Projective variety. B is projective. It is general as flag varieties are projective. This implies that the space of sections of this restricted line bundle over P mod B, so the space of sections of a trivial line bundle are just functions, scalar valued functions. And since the base variety is projective, there are only constant functions. So the space of sections is just canonically identified with a typical fiber, with k sub minus lambda, only constant functions. So maybe let me try again to draw some picture for you. So, excuse me, this is not that good. Maybe here. So we have this G mod P, partial flat variety, over which we have G mod B with the projection map, pi. So let me draw this G mod B. That is this guy. And these are the fibers. So this is maybe the typical fiber, P mod B. This bold line stands for the typical fiber, P mod B. And we have the line bundle over G mod B, the homogeneous line bundle induced by the character minus lambda. Let me draw the fibers of this line bundle. So these are the fibers of this line bundle. At any point of G mod B, and also here, and also here, here, everywhere. So what we have proved just now, we have proved that the restriction of this line bundle on this fiber, and actually on each fiber, because all fibers are just permuted by the group action, everything is equivariant. The restriction of this line bundle over this fiber of pi is a trivial bundle, and the only sections of this restricted bundle are constants. What does it mean? This means that not only the line bundle L sub minus lambda is the pullback of the line bundle L sub P comma minus lambda. This is obvious because what is the pullback? This means that you take fibers of the line bundle on the base on G mod P and pull them back to inverse images of points on G mod P. So if you have a fiber on which P acts as minus lambda on some point of G mod P, say on this point, then you just pull back this fiber to every point in the pre-image, in the inverse image in this fiber P over B. And the same holds for any fiber. So this is obvious from construction. But the computation which I did here shows also that the space of sections of this line bundle L minus lambda over G mod B is the pullback of the space of sections of this line bundle on the base on G mod P. The sections which are pulled back from the base are those which are constant along fibers. But as we have proved, all sections are constant along fibers. So this equality is true. And now we can just apply the Borel-Weil theorem for G mod B. Now apply Borel-Weil theorem for this line bundle on G mod B, and we get the statement which we want to prove. So this is the proof. This is the end of the proof. Okay, any questions? Let me maybe give you an example. So take for Y just the projective space, n-dimensional projective space. It is a partial flag variety for GLN, or better to say for GLN plus 1. It is a homogeneous space, the quotient space of GLN plus 1 modulo a parabolic subgroup pi, which is, what is pi? So pi consists of the matrices of the following form. You have something non-zero in the upper left corner, something non-zero here. And you have zeros in the first column, except for its upper entry. And you may have everything here. Well, of course, this should be an undegenerate matrix, since we are speaking about a group. And everything here. Okay, so this is a parabolic subgroup, which is the stabilizer of the point in Pn, given corresponding to the first vector of the standard basis in Kn+1, in the n+1 dimensional column vector space. And over this Pn, we have a collection of line bundles, which we already considered before, denoted O of M. Recall that this line bundle O of M is defined as follows. Its fiber over any given point in a projective space is just the space of homogeneous functions of degree M on the line in the n+1 dimensional vector space corresponding to this point in Pn. We have considered this this line bundle, I guess, on P1 in my first lecture, but on Pn the definition is exactly the same. And this line bundle is a homogeneous line bundle, which in my previous notation can be written as follows: L sub pi with character minus M epsilon 1. So if you recall the notation from my previous lecture, from my lecture on Monday, then you may remember that epsilon 1 is a character of the maximal torus consisting of diagonal matrices, which just takes the first diagonal entry of a matrix, of a diagonal matrix. And this is the character by which P acts on the line spanned by these first basis vectors. But when you are taking functions on this line, then the characters are inverted. So the action of the space of functions is given by the inverted character, minus epsilon 1. This is for the space of linear functions. And when you take the space of functions homogeneous of degree m, then you take this character to the power m, or in the additive notation, you multiply it by m. So this is why this classical line bundle on the projective space is a homogeneous vector bundle, homogeneous line bundle corresponding to this character, minus m epsilon 1. And now my theorem, the corollary of the Borel-Weil theorem, which was on the previous slide, says that the space of sections of this line bundle on Pm which is of course nothing but the space of homogeneous polynomials in projective coordinates x0, etc., xn, homogeneous polynomials of degree m. This space carries on an irreducible representation of GLN plus 1 with the highest weight m epsilon 1. Well, maybe not m epsilon 1, but rather m epsilon, excuse me, I'm cheating a little bit. It is, well, let me write it like this, m epsilon 1 star. This is just the corollary of the parallel theorem, which was on the previous slide. And actually, epsilon 1 star is just minus epsilon n plus 1. Maybe I used bad notation for the projective coordinates because I enumerate basis vectors by numbers from 1 to n plus 1, and the projective coordinates are enumerated by numbers from 0 to n. Let me change this notation. Let me enumerate from 1 to n plus 1.
I'm sorry, Professor.
Yes?
What's the epsilon 1 here means?
I will recall it in a minute. Okay?
Okay.
Just let me write down this.
We defined n.
So, excuse me. Let me first answer the previous question. So let me recall that epsilon I is a character of the diagonal torus, which takes a diagonal matrix of this form. Now it is of size n plus 1 to its ith diagonal entry, to Ti. Okay, this is a character on the diagonal torus. And so epsilon 1 takes value T1 on this diagonal matrix. I think that I answered this question, right?
Yes.
And it seemed to me that there was another question. Was there any question?
No, I want to ask how to deduce that the dual of epsilon 1 is minus epsilon n plus.
Well, actually, in this case, it is easy because what is the dual of the space of homogeneous polynomials in coordinates on a vector space? It is just the symmetric power of this vector space, the nth symmetric power. So let me write it down here, maybe some digression. So if you take the dual space of this guy, the dual, then it is just the symmetric, the nth symmetric power of k to the n plus 1. And here you can easily pick the highest weight vector. It is just the first basis vector to the power m. This is highest weight vector, because it is stable under the action of the Borel subgroup of upper triangular matrices. This, I mean, the line spanned by this vector in this symmetric power is preserved by the action of the Borel subgroup. So this is the highest weight vector, and its highest weight is clearly m epsilon 1, because epsilon 1 is the weight of E1 by the action of this torus. And now the highest weight of the dual space, oh, excuse me. I think yes. I mean, no, I'm sorry. I explained a different thing. I explained just this equality, maybe in different terms. I explained that this space is dual to the space with highest weight m epsilon 1. This is not what you wanted to see. I'm sorry. Let me erase this. So your question was why this irreducible representation has highest weight minus epsilon n plus 1. This is because here the highest weight vector is just x n plus 1 to the power m. So this function is preserved by the Borel subgroup by upper triangular matrices up to a multiple. So the line is preserved. This means that this is the highest weight vector, and its highest weight.
I did not understand why it is highest weight.
Because this line spanned by this vector in the space of polynomials of degree m is preserved by B. So when B acts on the space of polynomials,
on the right, right?
No. I mean, what do you mean by on the right? So the action is as follows. So an element of B acts on a function, on a polynomial.
Acts on the vector inside at what?
Yeah, yes, exactly. So this is the formula for the action. And now, if you take for f, so if you take for f the n plus first coordinate function. So this notation is a bit confusing, but I hope that you understand what does it mean. Then you just take, let me write it like this. You just take the n plus first coordinate of this guy. But it is easy to see that when you act by an upper triangular matrix on the column vector, then the last coordinate just is multiplied by some scalar. And this scalar is the inverse to the lower right corner element of this matrix, so to this guy. So this means that the character is minus epsilon n plus 1. This is for linear functions. And when you take the mth power, then you just multiply by the mth power of the character.
I did not understand where the minus come from. Well, I want...
Minus means inverse. Minus is the additive notation for inverse. It comes from this inverse.
Oh, in the additive notion. Oh, yes.
Exactly. This is in the additive notion, of course. In the additive notation. Yeah.
Well, but I think you define the action was the action on the right. Well, like G action on F. The value of G action on F at X is the value of F at X times G. Like this.
Well, I mean, the action on the right appeared at some point when I considered functions on G, on the group. But now I consider functions on a homogeneous space, on here, on this guy.
Oh,
and
right.
here everything acts on the left. So GLN plus 1 and all subgroups in GLN plus 1 act on this Y on the left. So this is a correct formula. Okay? Well, this was about line bundles on flag varieties or generalized flag varieties. But what if we take an arbitrary homogeneous variety? In general, the representation of a reductive group G on the space of sections of a line bundle over a homogeneous variety, say G mod H, In general, it is reducible. So let me write it down that in general, the representation of G in the space of sections of a homogeneous line bundle over some G mod H associated with some character chi of H, as we wrote before. In other notation, it is the induced representation. The representation induced from this character chi. In general, it is reducible. But since it is completely reducible, or semi-simple if you like, it decomposes into the sum of irreducible representations. And so it is a reasonable question to ask what are the multiplicities for irreducible summates? Multiplicities. These multiplicities, I will denote such a multiplicity in the following way. So it is more or less standard in the representation theory. So this is a representation. In my case, it is this representation space. This is a representation space. In my case, it is the space of sections of some homogeneous line bundle. And when I want to write the multiplicity of an irreducible representation, say of highest weight lambda in this space, I write it like this with a division sign. And this multiplicity can be computed using Frobenius reciprocity law. So this multiplicity is just the dimension of the space of G module homomorphisms from this irreducible G module, V of lambda, to the G module which we consider, this induced G module in my case. This is because of Schur's lemma. We already used it in the proof of Borel-Weil theorem. Because this V of lambda under a G module homomorphism, this V of lambda maps to the sum of irreducible submodules here. And actually, those irreducible submodules which are non-isomorphic to this one, they are not touched by this map. Because by Schur's lemma, a map from this guy to any non-isomorphic irreducible submodule of different highest weight is 0. And the map from this guy, any map, G module map from this guy to a direct summand in here, which is isomorphic to V of lambda, is just a scalar map by Schur's lemma. And so there are as many independent, linear independent homomorphisms, G module homomorphism from here to here, as many there are irreducible summands in the decomposition of this space, which are isomorphic to V of lambda. So I explained this equality. And now this dimension can be computed using Frobenius reciprocity, of course. Because this is just by Frobenius reciprocity. This is just the same as the dimension of the space of H module homomorphisms from V of lambda, from the same V of lambda, but now considered as an H module, to this one-dimensional H module K sub chi given by the character chi. And again, we can swap the arguments of this in this homomorphism space by replacing each homomorphism to the adjoint linear operator with the adjoint linear operator, and we get the same space and the same dimension, of course, as the space of H module homomorphisms from the dual H modules in the opposite direction. So this is from K sub minus chi to V of lambda star. And this space is, of course, so we have to compute the dimension of this space, and this space is, of course, nothing but the space of H semi-invariant vectors which I denote like this, of eigenweight minus chi. Because what is written here on the left, it is just the one-dimensional space on which h acts by a character minus chi, or chi inverse, if you like, in the multiplicative notation. And each such a vector to an eigenvector in. So this is just this space of homomorphism is just the space of eigenvectors for h with eigenweight minus chi on this vector space. And by the way, we see in particular that this dimension is because v of lambda star sections of any summands are finite, and we computed these multiplicities. So actually, it is a fundamental problem in harmonic analysis on homogeneous. Yes, any question?
I think I have a network problem. So what did you just say?
Well, how many minutes ago? I mean,
just no more.
Just now, I have said that we have proved by this computation that the space of sections of any homogeneous line bundle on any homogeneous variety is maybe a reducible G module, but the multiplicities of irreducible summands are all finite. And it is a problem, a fundamental problem in harmonic analysis on homogeneous varieties, on homogeneous spaces, harmonic, non-commutative maybe harmonic analysis, generalized harmonic analysis.
Yes, now I understand.
The fundamental problem in harmonic analysis is to compute, to decompose, maybe better to say, to decompose the representation of G in sections of homogeneous line bundles over a homogeneous space, to decompose it into irreducible representations. On a line or on a circle in Fourier series. The setting of algebraic groups as follows. So you are given a homogeneous space, you are given a homogeneous line bundle over this homogeneous space, you get a representation of G in the space of sections, and the question is how to decompose it into irreducibles. Of course, this decomposition is unique only up to isomorphism, because if you have several occurrences of an of one and the same irreducible submodule in this decomposition, then inside this isotypic component, inside the sum of these isomorphic pairwise isomorphic irreducible submodules, you can change bases mean that every irreducible G module occurs in this space. But let's consider the situation when if an irreducible G module occurs in the decomposition, then it occurs at most once. In this case, the decomposition is just unique. And here we meet for the first time one of the main heroes of my course, that is spherical homogeneous spaces. So let me turn the page. And now I shall explain you what are spherical homogeneous spaces.
Well, why is the number does not exceeding 1 is the good case?
Because, as I said, that in this situation, the decomposition of this space of sections into irreducibles is unique, not only up to an isomorphism, it is just unique. The irreducible summands are uniquely defined subspaces in this big space.
Oh, yes, I see.
So it is a canonical way to decompose this space of sections into irreducible. Of course, it is nice if it is so. At least I believe it is nice. So now I have maybe 5 minutes before the break. Oh, no, more than 5 minutes, 8 minutes before the break, right? And let me explain you what are spherical homogeneous.
Professor, I think your network is not good. We are expressing
The problem is that so let me resume sharing. Is it better now? Do you hear me?
It's better. It's better now.
Well, let me for the future not switch on my video. Okay, so let me recall the basic notation. So G always denotes a connected reductive algebraic group. H, some closed subgroup in G. And let us also choose a Borel subgroup, B, in G. It is unique up to conjugation. We choose some. Okay. Also, I need a notation for Lie algebras of algebraic groups. We use lowercase German letters to denote Lie algebras of algebraic groups. In particular, let me denote by small German g the Lie algebra of big G, of big capital G, Latin capital G. This is just the tangent space at identity. Let me just recall you what is the Lie algebra of an algebraic group. It is a tangent space of identity, Lie algebra of G, which is well, you may consider G as a subgroup in some GLM, then this small German G is just a subspace in the tangent space for GLM in the space of matrices and by n matrices. And it is a Lie subalgebra with respect to the commutator of matrices. And also we have an action of the group G on its Lie algebra, which is called the adjoint representation. It is a linear representation. It is called the adjoint representation. Let me denote it in the standard way by adjoint representation. So if G is embedded in some GLN as a closed subgroup in GLN, then, as I said, G is a Lie subalgebra in the algebra of matrices and by n matrices, Lie subalgebra, where the commutator in this Lie algebra is given by the usual formula, the product in one order minus the product in another order for any psi and eta in G. This is
The network is done again.
these are standard things from the theory of algebraic groups. So I refer to those textbooks which I cited on my second maybe lecture, at the beginning of my second lecture. So definition theorem.
The network is still not good.
Y equal to G A.
Professor, we don't hear you.
Is that the Borel sum of G acts on Y with an open orbit. The second property is that there exists an element in G such that the sum of Lie subalgebras, the Lie algebra of the Borel subgroup, plus the Lie algebra of H, which there exists maybe another Borel subgroup, say.
Oh, Professor, what is condition 2? My network is too bad.
Let me repeat condition 2. If you replace the so these small letters are German letters corresponding to big Latin capital letters. So this H small is the Lie algebra of big H, and this B small is the Lie algebra of big B. So this condition says that if you replace the Lie algebra of H by some conjugate, then the sum of this Lie subalgebra with the Lie algebra of the Borel subgroup B is equal to the Lie algebra of the whole G. Okay?
And what does the condition 1 mean by open orbit? The orbit of a point is an open set.
There exists a point in Y such that the B orbit of this point is an open subset in Y.
Oh, we just need 1 point for it.
Yeah. Well, any point in this open orbit possesses this property, of course. So the condition is that there exists such an orbit. So the third condition is that there exists a Borel subgroup B in G, such that if you take the Lie algebra of this Borel subgroup and add the Lie algebra of H, then we get the Lie algebra of G. This condition is very similar to the second one. So let me maybe finish the list of conditions, and then we can make a break, maybe with a little shift. So the fourth condition is about B invariant functions. So it says that the field of B invariant rational functions on Y, which are invariant under the action of B, it is just the constant field, the base field K. There are no non-constant B invariant rational functions on Y. Now, the fifth condition is about representation theory.
Well, the condition 4 is the B invariant, right?
Yeah, B invariant. This this superscript B means upper index B means that you take B invariant elements, B invariant functions, stable under the action of B, fixed by the action of B. So the fifth condition says that for any homogeneous line bundle, say L over Y.
Hey, Professor, I want to ask a question about condition 4. You write and the left hand side is about function on Y or rational function.
The left hand side is about rational functions. This parentheses mean rational field of rational functions.
We allow poles.
Excuse me? We allow poles. We allow poles. You're right. So this fifth condition says that for any homogeneous line bundle over Y, the representation of G in its space of sections, well, maybe I put Y here, not G mod H, I put Y here. The representation of G in this space of section is multiplicity free, which means that each irreducible submodule occurs only once in here, at most once in here. So the sixth condition says that actually this is the same as the fifth condition, as we see soon. But it is a reformulation of the sixth condition, of this fifth condition. It says that for any dominant weight, say mu, for any dominant weight mu, and for any character of H, the dimension of the space of H semi-invariant vectors in this irreducible representation with highest weight mu, with character lambda, with character chi, with eigenweight chi, this dimension is always at most one for any mu and any chi. The seventh condition is a particular case of the fifth condition. It says that the action of G, the representation of G, in the coordinate algebra, in the algebra of regular functions on Y, is multiplicity free. And the final condition, the eighth condition, is actually a reformulation of the seventh condition. It says that for any dominant weight mu, the dimension of the space of H invariant vectors fixed by H in the irreducible representation of highest weight mu is at most one. But these two last conditions, 7 and 8, are equivalent to the previous 6 only in the case, so this is if Y is a quasi-affine variety. In this case, the conditions 7 and 8 are equivalent to the first 6 conditions. In the general case, they follow from the first 6 conditions, but are not equivalent to them. So this is a theorem that all these conditions, all these properties are equivalent, maybe under certain restrictions, if you consider properties 7 and 8. And also, this is a definition. So homogeneous varieties satisfying these conditions are called spherical. Now I'm ready to stop the first half of my lecture. I'm sorry for the internet problems. I don't know on which side were these problems, maybe on my side. I apologize, but anyway, I hope that at least everything is written here now. You can ask questions. Now we have a break for 10 minutes, so we resume at maybe 10 minutes or 11 minutes, 11 minutes to what? To 8, I guess, yeah. 11 minutes to 8. Okay, so any questions or comments?
Well, I want to ask some question about condition 6.
Yes, please.
Well, I think the eigenspace of a group is deduced from its action and its one-dimensional character. Right?
Exactly. This is already about the proof.
Well, for condition 6, the action is induced by mu, right?
Well, maybe by mu. No, I mean the action. So we consider the space of sections of a line bundle L induced from the character chi. This is a line bundle over G mod H over this guy. It is induced from the character chi in this 6th condition. And if you compute the multiplicity of this irreducible submodule.
Oh, I know. V mu is irreducible representation of G.
Of G, exactly.
I know. And chi is independent of mu, right?
Exactly. Chi is independent. So mu and chi are here chosen independently. This may be any dominant weight, and this may be any character. They are chosen independently, right?
Lambda h is denoted as a one-dimensional character, right? If I
Say it again. Lambda of h is the group of characters.
group of one.
This was my general notation for characters, maybe on the previous lecture. The group of characters is denoted like this.
Group of characters or one-dimensional characters, I think.
Well, what I call a character is a one-dimensional character by definition. So for me, a character is a homomorphism from H to the multiplicative group of the field.
Okay. Thanks. And I want to ask something about the joint representation.
Yes.
I think we have another representation for the adjoint representation that the adjoint the action of G on Casey of the Lie algebra is the value of the left invariant vector field induced by Casey at G minus and put back push forward through G.
Well, yeah. I mean, of course, you may define this adjoint representation in these abstract terms, but what is the advantage of algebraic groups, at least linear algebraic groups? The advantage is that everything can be embedded into matrices, maybe non-uniquely. There are different ways to embed a linear algebraic group into matrices, but if you do this, then everything is reinterpreted in terms of matrices. So in this under these embeddings, the adjoint representation which you described using vector fields, yeah, so is just given by this formula. So you can find this in any textbook on algebraic groups or on Lie groups.
Yes, I know this. I know this formula. I just want to ask whether we use the value at G minus pushed forward by G, or the value of G pushed forward by G minus.
This doesn't matter. This doesn't matter because left and right multiplication commute. You may multiply on the left, then on the right, and you may do it vice versa. So you may take a tangent vector, you may consider the right invariant vector field, and you may push it forward with respect to left multiplication. And you may do conversely. You may consider the left invariant vector field corresponding to this tangent vector, and you may push it forward by right multiplication. This is the same because left and right multiplication commute on G. Okay? Because of associativity of the group law, basically. So, more questions, comments?
Professor,
Yes.
it's the second one here. So the right is the Lie algebra of G, right?
On the right, yes. On the right, it is the Lie algebra of G, right?
And on the left, the first term is
Lie algebra of B. Lie algebra of B of this Borel subgroup.
So the second term is.
And this guy is the Lie algebra of H, to which we apply the adjoint operator, the conjugation with G. And actually, this guy is the Lie algebra of the conjugate subgroup. Maybe let me write it. Well, I don't want to write it here. Well, maybe I will write it here for you, but later on, I will erase it for the notes which I leave. So this guy, let me just finish. This guy is the Lie algebra of GH G inverse. Okay?
Okay.
Well, in condition 2 and 3, the sum here is the sum of vector space or the
Exactly. It is, yes, it is a sum of vector space. It is not, say, a direct sum of Lie algebras. It is not a direct sum, by the way. It is just a sum. They may intersect. The intersection may be non-zero. Just the sum of vector spaces. Okay. So we have maybe a couple of minutes left for the break. Maybe I'll leave you for this couple of minutes. I switch off my microphone. Well, I think that we can continue after this 10 minutes break. We can continue. Well, now we have not that much time left for the proof of the theorem that all these conditions are equivalent, but I hope to manage at least with some of equivalences. Let's turn to the proof. Well, first, let me explain why the first condition is equivalent to the second condition. Just for you to recall that the first condition is that the Borel subgroup, the chosen Borel subgroup B, acts on my homogeneous space Y with an open orbit. And the second condition is that if we replace the stabilizer subgroup H by its conjugate and take a sum of the Lie algebras, the Lie algebra of Borel and the Lie algebra of this conjugate stabilizer, then we get the Lie algebra of the whole group. Why these two conditions are equivalent? This is not hard to explain. So indeed, what do we have? We have that, well, suppose that first condition holds. So suppose that the orbit, the B orbit of some point Y in big Y is open. This point Y is obtained from the base point, which I denote by X. X is a point in Y whose stabilizer is equal to H. So if you identify Y with the coset space G mod H, then X is just the coset of unity. But actually, you can take any point with stabilizer H. So suppose that for some another point, Y in big Y, this orbit is open. This is if and only if and only if the following product set B times G times H is open in G. Because Y is a quotient space G mod H, and a set in Y is open if and only if its inverse image in G is open, because of quotient topology. And this holds if and only if another product set G times G H G inverse is open in G. You just can multiply what is written on this line by G inverse on the right. So now finally, this latter condition is equivalent to the condition 2. So this is if and only if and only if the Lie algebra of B plus the Lie algebra of this subgroup in brackets, this is conjugate Lie subalgebra, the sum of these two Lie subalgebras equals to the Lie algebra of G. Well, why so? Maybe it's clear to you, but anyway, let me say a few words. This is because you can differentiate the multiplication map from B cross GH G inverse to G, the multiplication map you can differentiate this map at unity. And when you differentiate the multiplication map on the group level, you get the addition map on the Lie algebras level. And so if this set, the image of this multiplication map is dominant, is open, then this means that the tangent map is an isomorph. The tangent map, the differential of the multiplication map is surjective. This means exactly that the sum of the Lie algebra of this guy and of the Lie algebra of this guy is the Lie algebra of G. Okay? So this is an explanation for this equivalence. Now we have proved that the first and second condition are equivalent. As for the third condition, why it is equivalent to the second one? Well, it is almost obvious. Let me switch to the previous slide. So look at the equality in the second condition and apply the adjoint action of G inverse. Then B is replaced with the conjugate of B. And on the level of groups, this means that you just take for B prime another Borel subgroup, the following conjugate subgroup: G inverse times B times G. And if you take this B prime, then again, let's look what happens. if you apply the adjoint operator corresponding to G inverse, the conjugation, yes?
Shouldn't we choose G times B times G inverse and not G inverse times B times G?
On which line? Here?
The last line.
Yes, just as written here. Because if you conjugate B with G inverse, let's remember this. If you conjugate with G inverse, then the second summand, this guy, just turns again to H, to the Lie algebra of H, right? You come back to the Lie algebra of H. And this guy...
I misunderstood condition 3.
Yes. When you deduce 3 from 2, you conjugate with G inverse. And when you deduce 2 from 3, then you conjugate with G. So you conjugate in different directions by 2 mutually inverse elements of the group. Is it clear? Okay. So this proves that the second and third conditions are equivalent. Now, what about the fourth condition? Let me explain why it is equivalent to the previous condition, say to condition 1. It is easier to explain why 1 implies 4. This is just because of the following. Take any B invariant rational function on my homogeneous space. Since this function is B invariant, it is constant on the open orbit. It is constant on each orbit where it is defined. But since it is a rational function, it is defined somewhere, and in particular on some open subset. And in particular, it has to be defined on the open orbit, because my variety Y is irreducible. And this means that any 2 open subsets intersect. So if F is defined on some open subset, and if it is B invariant, it has to be defined on the open orbit, and it has to be constant on this open orbit because it is invariant. And therefore, it is constant also on the closure. Therefore, it is constant also on the closure of this orbit, which is just the whole Y, because every open non-empty subset is dense in an irreducible variety Y. Okay, now we proved that every B invariant rational function is constant, provided that you have an open orbit. Let's prove the opposite direction. So Y4 implies 1. Here we use a theorem from algebraic groups theory, or from invariant theory, if you like, called Rosen-Licht theorem. It's a general theorem which I will not prove. I just formulate it for you. Rosen-Licht theorem. Rosen-Licht theorem says, it is more general than our situation. It says that if you are given an action of any algebraic group B on any irreducible algebraic variety Y, so Y is any irreducible variety, and B is any algebraic group acting on Y. I do not assume that Y is a homogeneous space for some bigger group. I do not assume that B is solvable or connected, nothing. I only assume that Y is irreducible. Then under this assumptions, there exists an open, non-empty open subset U in Y such that for any 2 points in this open subset which lie in different orbits, there exists a rational function on Y which is B invariant, a B invariant rational function on Y, which distinguishes these orbits. So this means that it takes different values in X and in Y. So briefly speaking, Rosenlicht theorem says that general orbits are separated by rational invariant functions. Orbits of general position or orbits in an open subset are separated by invariant rational functions. This is the Rosenlicht theorem. And in our case, we apply this Rosenlicht theorem to our homogeneous variety Y. Assume that property 4 holds. This means that there are no non-constant invariant rational functions. Only constants are invariant rational functions. This means that for any Y in this open subset U, where the orbits are separated by invariant functions, for any point Y in this open subset, its orbit contains the whole U. Because, let me turn again to the previous page, because in this U, orbits are separated by rational invariant functions. And if there are only constant functions, which are invariant, then points cannot be separated by values of these invariant functions. And this means, by Rosenlicht theorem, by this statement, that they lie in one and the same orbit. So this means, in particular, that since the B orbit of this Y contains an open subset, it is itself open. This is exactly.
Why can we deduce that it is self-open?
Well, because if an orbit contains an open subset, this means that
we can translate it by the group action.
Exactly. The whole orbit is just the union of all translates of this U by elements of B. So if you take U is a neighborhood of Y contained in this orbit. And if you translate this neighborhood by all elements of B, you get the whole orbit. This means that this orbit is the union of translates of U, the union of open subsets, and then it is itself open. Okay? So we have proved that the fourth condition implies the first one. Therefore, the first 4 conditions are equivalent. Now let us turn to the multiplicity-free conditions. So let's explain why condition 4 implies condition 5. Recall that condition 5 says that for any homogeneous line bundle over Y, the representation of G in the space of sections of this bundle is multiplicity-free. Why so? Let's explain this. We argue by contradiction. by contradiction. So assume that we have two occurrences of one and the same irreducible submodule in the space of sections, say subspaces M1 and M2 in the space of sections, which are G-invariant subspaces, and the representation of G in both subspaces is isomorphic to one and the same irreducible G module V of lambda of highest weight lambda. And these subspaces, though they are isomorphic, they do not coincide. They are different subspaces. So the multiplicity of this V of lambda in the space of sections is at least 2. Assume that. Now let us choose highest weight vectors in both subspaces, say Si in Mi. I use the letter S because it is a section, actually. These are highest weight vectors, which means that they are eigenvectors for the action of B with one and the same eigenweight lambda. And then we may take the ratio of these two sections. We may consider F, which is S1 divided by S2. The ratio of two sections of a line bundle is already a function, a scalar valued function. And this function is B invariant. Because when you act by B, the numerator and denominator of this fraction is multiplied by one and the same character. And these two multiples cancel when you divide the numerator or by the denominator. So the ratio is an invariant function, but it is non-constant. Because these two sections are non-proportional. They lie in different subspaces, which actually intersect in 0 because they are irreducible G submodules. The intersection is 0. Let me write it maybe for your convenience. They intersect in 0. So the ratio of these two different sections is not constant, and this is a contradiction with the assumption of 4. Thus, we have proved that condition 4 implies the multiplicity-free condition 5. Now, instead of proving that 5 implies 7, let me first, that 5 implies 4, the reverse direction. Let me first prove that 5 implies 7. So the condition 7 in here is that the action of G, the representation of G in the space of in the algebra of regular functions on Y is multiplicity free. But what is the algebra of regular functions on Y? It is just the space of sections of the trivial line bundle over Y. Functions are sections of the trivial line bundle. So to prove that 5 implies 7, you just have to take for this line bundle L, the trivial line bundle, which I denote by O sub Y. So in this notation, just by abuse of notation, I denote the trivial line bundle by the same letter as its sheaf of local sections, which is just the structure sheaf, the sheaf of functions on Y. So this is usually a usual thing when you consider line bundles or vector bundles. You identify them with the sheaves of sections.
why
of
it
those
is
exceptions.
a homogeneous line bundle?
Yeah, Y always means my homogeneous space, just as in the formulation of this theorem. It is a homogeneous space G mod H. So G is the acting group.
No, I mean,
yeah.
why is the trivial line bundle a homogeneous line bundle?
Why the trivial line bundle is homogeneous? It is associated with the trivial character of H. So when you act on the fiber just trivially, then you get a trivial bundle. So the action of G on the total space is only coming from the action on the base. The action on the fibers is trivial. Okay. So this implication holds for any Y. Here I don't assume that Y is quasi-affine. But now let me deduce condition 4 from condition 7. In the case when Y is quasi-affine. So now my assumption is that Y is quasi-affine.
So will we prove that 5 implies 4 without the condition that Y is quasi-affine?
We have proved that 5 implies 7, not 4. To prove that 5 implies 4, we have to assume that Y is quasi-affine, but we go through the condition 7. We prove that 5...
You said that the first 5 conditions are always, first 6 conditions are always equivalent whenever...
Exactly. I will come to the condition 6 later.
So will we prove 5 implies 4 without the condition that Y is quasi-affine?
We shall prove that. But a bit later. So far we proved that 4 implies 5. Then we prove that 5 implies 7 under assumption of quasi-affinity. After that, we prove, we prove that 5 implies 7 without any assumption. Excuse me, just a minute. I erase the drop of ink which I put here. Okay. We proved that 5 implies 7 without any assumption.
There is an empty page.
Yes, but I mean, let me erase it. I'm sorry for mess. What is this? I don't know. Let me erase this empty page. Okay. And then let me turn back to my last page. So now I want to prove that 7 implies 4. And this I do under assumption of quasi-affinity. Okay? So what can I do? Since Y is quasi-affine, this implies that the field of rational functions on Y is the fraction field of the algebra of regular functions. Okay? In particular, if I take any B-invariant rational function, say f, I can represent it as a ratio of 2 polynomials, say P1 over P2. Okay? These PIs are polynomials, regular functions on the whole Y. And also I can write this previous equality in the following way. P1 equals to F times P2. So F is just a rational function, but P1 and P2 are regular functions. Now what can I do? I can consider how my group B, Borel subgroup B, acts on the algebra of regular functions. We have a representation of B in the space of regular functions. And I can take the orbit, the B orbit, of the polynomial pi in this space of regular functions, and I can take the linear span of this B orbit, the linear span over K. Let me denote this subspace as M sub I.
Hey, well, I want to ask a question.
Yes.
The action of G on Ky is the right multiplication or inverse and left multiplication?
No, it's by left multiplication, because what is y? Y can be identified with the space of left cosets over H, and on this guy Gx from the left. And this action induces the action on functions. This is an action on the left. Okay? And also B acts on the left as a subgroup in G. Okay. So let me consider this vector space. This is a B-stable subspaces of finite dimension. So B-stable, B-invariant subspace of finite dimension. This again follows from the general properties of algebraic group actions on algebraic varieties. I refer to the textbooks for this statement. So this is a B-stable subspace of finite dimension, and we have a linear representation of B in each of these two subspaces, M1 and M2. And now let me recall a theorem from algebraic groups called Lie-Kolchin theorem. Lie-Kolchin theorem. Lie-Kolchin theorem says that given a linear representation, say B in M.
What is the second person name? Kolchin.
Kolchin. Kolchin. Kolchin. This is a mathematician of the first half of 20th century, American mathematician. Emil Kolchin. I'm not sure about the name, but the surname is Kolchin. Okay, so this theorem says that given a linear representation of a connected solvable algebraic group, of a connected solvable algebraic group in some vector space M. This group I again denote by B because I want to apply this theorem to my Borel subgroup. So given a linear representation of a connected solvable algebraic group, there always exists a B-stable line spanned by some non-zero vector M in this big M. By the way, this is the reason for existence of highest weight vectors in irreducible representations of reductive groups. This stems from this theorem. So if we apply the Lie-Kolchin theorem to our situation, then we can find an eigenvector for B in the second space M2. Let us choose this vector. Choose, say, Q2, an eigenvector for B in the space M2 of some eigenweight lambda. Let me remind you that M2 is the span, the linear span of the B orbit of P2. So this eigenvector Q2, Q sub 2, is a linear combination, sum over some i's, some scalar multiples, alpha i's, times B i's applied to P2. So in this formula, alpha i's are scalars, and b i's are elements of my Borel subgroup B. So choose such an element Q2, and then if you consider a polynomial Q1, which is obtained from P1 by taking the same linear combination. So let me define Q1 by definition. Let it be the same sum alpha I times bi applied now to P1. Then this guy is just equal to f times Q2 because let me remind you that P1 equals to f times P2, and when you act by these elements Bi, f doesn't change because f is invariant, and you get that you get the same equality for by P1 and by P2, and then when you take the sum, the linear combination, then this property is preserved. So Q1 is f times Q2, and since Q2 is an eigenvector for B with eigenweight lambda, and f is B invariant, then Q1 is also an eigenvector for B, now sitting in M1, but with the same eigenweight. So what did we get? We get two eigenvectors, yes?
Eigenvector, yes, I know.
Okay, so we get two eigenvectors of one and the same eigenweight in the algebra of two eigenvectors for B with one and the same eigenweights in the algebra of regular functions over Y. By the way, here I wrote here, for some reason, I don't know why, excuse me for that, I replaced Y with X. Here it should be Y, of course, not X. Sorry for this typo. And since we have found, let me write it down, that QI's are highest weight vectors in G submodules spanned by these highest weight vectors. So a G submodule, say Ni, is a linear span of the G orbit of Qi. It is a G submodule in the algebra of regular functions with the highest weight, with one and the same highest weight lambda. So both of these G submodules are isomorphic to V of lambda. Now, since we are proving that condition 7 implies condition 4, we assume condition 7. This means that we assume that the action of G on the regular functions over Y is multiplicity free. Since we have found two irreducible submodules of one and the same highest weight, then they have to coincide. This implies that N1 is equal to N2. And by the uniqueness of the highest weight vector up to a multiple, this means that Q1 and Q2 are proportional. That is, their ratio, which is F, is just constant. And this is the condition 4, which we wanted to prove. This is the condition 4, which we wanted to prove. So we have proved that under a quasi-affinity assumption, condition 7 multiplicity freeness in the regular functions over y implies condition 4, that there are no non-constant rational invariants. And now if we drop the quasi-affinity assumption, then the proof can be given, the main idea of the proof is basically the same as in the quasi-affine case. The only problem is that if y is not quasi-affine, then there may be too few regular functions on y. For instance, if y is projective, then there are only constant regular functions, and they are not enough to generate the field of rational functions. But there are always enough sections of line bundles to generate all rational functions. So this is the idea. And now let me explain how this idea works. So now let me prove that condition 5 implies condition 4. Condition 5 is a multiplicity-free condition for all line bundles. Let me prove that condition 5 implies condition 4 without any quasi-affinity assumption. So let me recall the Chevalets theorem. Y is a homogeneous space of a linear algebraic group G. And this means that there exists a linear representation of G on some vector space V such that my homogeneous space Y is represented as an orbit in this in the projectivization of this vector space, an orbit of some point in the projective space, projectivization of V corresponding to some vector V small in V. Okay? Now what can we do? Suppose we have a rational function on Y, a rational function, excuse me, parentheses, not square brackets, which is B invariant. We want to prove that this function is constant. This is a function on a quasi-projective variety embedded in a projective space. This function can be represented as a ratio of two polynomials in projective coordinates, P1 over P2, where these PIs belong to the algebra of polynomials on the vector space V, which are homogeneous of some degree m, one and the same degree m. So the ratio should be of degree 0.
Hey, Professor, I think
Yes.
the first line will with y equals the orbit of some point in the projective space only happens when y is quasi-projective.
But any homogeneous variety for a linear algebraic group is quasi-projective. This is a theorem which I stated on the
Yes,
second
you
lecture, I
said
guess.
the quotient of an algebraic group by its closed subgroup.
It is if you take a linear algebraic group, it is always quasi-projective. I guess that even without linearity assumption. As far as I remember, the quotient of any algebraic group over its subgroup, its closed subgroup, is always quasi-projective. But for linear algebraic groups, there is a more precise statement which is formulated on the first line. There is a representation of G in some vector space such that this homogeneous variety is realized as an orbit is in the projectivization of this representation. This is a Chevalets theorem, which I stated at the second lecture, I guess. And you can find this theorem
Yes,
in...
you stated that, but you didn't write the name of the theorem.
I'm sorry. Let me write it. Let me write it now. Maybe. So a theorem of Chevalets. Okay. Well, we represented a rational function on my homogeneous space as a ratio of two polynomials in projective coordinates. These homogeneous polynomials, of course, they are not functions on the projective space. And also they are not functions, the more so they are not functions on Y. Only their ratio is a well-defined function. But these polynomials, well, they are sections of a vector bundle, of a line bundle, this O of M. And basically, we can do with these polynomials the same thing, which we have done when we proved that condition 7 implies condition 4 under quasi-affinity assumption. What we can do, so let me write that as before, we can replace these polynomials with the other two polynomials, say Qi's, which are not just homogeneous polynomials of degree m, but which are also semi-invariant with respect to the action of the Borel subgroup. Again, here we use the Lie-Kolchin theorem. However, as I said before, these polynomials, or better to say their restrictions to Y, can be considered as sections of a homogeneous line bundle. So Qi restricted to big Y, let me denote it as Si, they are sections. They are sections of a homogeneous line bundle L, which is just the line bundle O of M over the projective space restricted to Y. And these are not just sections, they are B semi-invariant sections of one and the same eigenweight, because their ratio is a B invariant rational function, as before. This means, as before, that these two guys are highest weight vectors in some irreducible G submodules and I in this space of sections, which are isomorphic to one and the same irreducible G module V of lambda. And again, since we assume multiplicity-free condition, these two submodules have to coincide, which means that the function f, which is the ratio of the sections S1 and S2, the highest weight vectors in these two submodules, has to be constant, because a highest weight vector in an irreducible G module is unique up to proportionality. Okay, so we have finally proved that the first, let me turn back to the formulation. We have finally proved that conditions 1, 2, 3, 4, 5 are equivalent, and under quasi-affinity assumption, they are equivalent to the condition 7. As for the remaining two conditions 6 and 8, let me finish the proof by saying that the equivalences of 5 and 6 and 7 and 8, these two equivalences, they follow from computation of multiplicities, which we did at the end of the first half of my lecture. So computation of multiplicities. Namely, we have found that the multiplicity of an irreducible submodule in the space of sections of a homogeneous line bundle associated with the character chi, excuse me, let me put lambda here, is equal to the dimension of the space of eigenvectors for H, acting in the dual irreducible module V of lambda star, eigenvectors for H with eigenweight minus chi. This we have proved. And now conditions 5 and 7 say something about that multiplicities are at most 1. And conditions 6 and 8, let me turn to these conditions, say that these eigenspaces of some characters, so here mu stands of lambda star on the last page, are at most 1. The dimensions of these eigenspaces are at most 1. So this is the same condition as here, as written here. Now we have proved that all conditions of the theorem are equivalent. This is the end of the proof of this theorem, which defines the class of spherical homogeneous spaces. As for examples, they will follow on my next lecture. And sorry that I took 5 minutes after the end of my time. Sorry for 5 minutes, for being 5 minutes late. Thank you for your attention. If you have some questions left, then please ask.
If I have some question about condition 8, what
Yes.
What do you mean by the upper right H?
Well, exactly the same as here, for instance. The space.
Right? You mean
The space of
not eigenspace.
Not eigenspace. The space of H invariant vectors, vectors fixed by H. But this is the same as the space of eigenvectors of eigenweight 0. Or if you in multiplicative notation of eigenweight 1. Because what is a vector of eigenweight 1? It is a vector fixed by the action, right? So this guy actually is a particular case of this guy. In the case chi equals to 1 or to 0 in the additive notation. Okay? More questions? Or comments? Well, maybe this proof was a bit lengthy because, I mean, there are too many conditions defining this class of spherical homogeneous spaces. But this is the reason why these homogeneous spaces are so interesting. They are characterized in many different ways, which are not related to each other at the first glance. That's why they arise in different areas, and as we shall see in the following lectures. As for examples, of course, you want to have examples. Actually, you had some examples before, but maybe you do not guess yet that these were the examples for spherical homogeneous spaces. But I will start the next lecture on Monday with examples.
One last question: why do we call them spherical?
This will come from my first example on the next lecture. So maybe let me ask you to be a bit patient and take a pause till Monday. On Monday, at the beginning of the lecture, I will answer your question. Okay? More questions? Comments? Suggestions? Anything? Well, if not, let me maybe stop sharing. The notes will appear soon in the storage as usual. So if there are no more questions, then let me say goodbye to all of you and see you on Monday, next Monday. Bye-bye.